Hi, today we're going to get more into an application of Lewis structures and talk about our first type of chemical bonding. First, to get us started, I have a video here about a reaction that you may or may not have seen before, but one you should be familiar with the outcome of. So write down any questions you have as they occur to you.
So this is my little setup to make some table salt, also known as sodium chloride. So just from the name sodium chloride, you can pretty easily see that it has two major components, sodium and chlorine. On their own, both elements sodium and chlorine are pretty reactive and dangerous. However, interestingly enough, when they are combined, they form a nice edible salt. This is an interesting demonstration that shows how drastically different the properties of a compound can be compared to its components. So for the first step, I'll cut off a small piece of sodium that I'm going to be using for the reaction. Sodium metal is actually quite shiny, but it quickly reacts with air and moisture and forms a white coating. You can see a bit of the shininess after it's cut on the bigger piece. The liquid that you see dripping off the sodium is mineral oil, which is what the sodium is stored in. This is my chlorine generator. Inside the flask is chlorine pool pellets. I then poured hydrochloric acid into the flask and it reacts to produce chlorine gas. As you can see, the chlorine has a faint greenish yellow color. The top is blocked, so the chlorine is forced down the hose. The hose leads into a larger flask with sand at the bottom. The sand is at the bottom to prevent the glass from cracking from high heat. Inside the flask is then dropped a small pellet of sodium. This is half of the piece that I cut off in the earlier shot. A little water was added to get the reaction started, but I think I added a bit too much. The white cloudiness that you see is a suspension of really small particles of sodium chloride. The white stuff on the walls is also sodium chloride. When a lot of the sodium chloride cloud has dissipated, it's a lot easier to see a lot of the white sodium chloride all around the flask.
I'll upload the whole video in case you wanted to watch how that all turned out. So I wanted to look at potassium. I know sodium, we'll talk about sodium in a little bit. Potassium, of course, is in group 1 with sodium. So you can see a lot of the same things happening. We saw from a previous video that potassium put into water explodes much the same way the sodium does, just with a slightly different color due to different energy levels, but the reaction proceeds in much the same way in terms of how the atoms interact. So that would mean that potassium is explosively reacted with water, and then, potassium's in bananas. I've heard that before too. So really there's a big difference between the potassium atom and the potassium ion, which is what is in the bananas that you're talking about. Typically, it's we don't always use the full name of everything when we're talking about it just in conversation. So sometimes a little bit of information is lost there. But something to think about is why we have a +1 listed as an oxidation number, which is related to ionic charge, but not the same thing. And why would potassium be making that +1 ion? If you remember from the periodic table, things that are on the left side of the periodic table typically have low ionization energy and low electronegativity. This means that for this potassium ion, we are most likely to be losing electrons and unlikely to be gaining electrons. So no gain, yes to lose. And that is just that information. This one electron that is the outermost electron is the one that is lost. Remember that due to shielding, the effective nuclear charge is a +1 on that fourth energy level, so it's relatively low and it's relatively far away, so that one electron just does pop off. You may notice too that once the ion gets made, the ion that's left behind now has 8 electrons in its outermost energy level. We're not going to refer to energy level 3 for potassium as the valence shell. It's always going to be relative to the atom. It'll always be 4. So what we would say is for the potassium ion, it has an empty valence shell, not 8. We'll see that in execution on the next slide. But this may be where you've heard the octet rule invoked before, this idea that 8 is a magic number. It is and isn't. You'll see a little bit more on the next slide, but if you want to latch onto it, the general rule is that many atoms will lose or gain electrons such that they make an ion that's more stable electronically than the atom that you started with. It just turns out that 8 is a number that shows up frequently when that happens. So yes, the idea here is that both sodium and potassium have this one electron, but you'll notice that I'm just going to circle the valence in each case. You'll notice that the next level down is frequently what we're going to be looking at when you're losing electrons, and now we have that 8. If potassium becomes potassium plus, its electron configuration as the ion is 288, which matches a noble gas. If sodium was to become a sodium ion, its new electron configuration would be 28, and it would match, well, it doesn't match argon, it matches neon, the next one above. So stable ions, we look at these numbers here, and stable ions seem to, A, have 8 electrons in their outermost energy level, and B, they seem to match a noble gas. And those two things are related because we know that noble gases don't chemically react with anything. So the sodium ions in salt chemically are more similar to a neon atom than they are to a sodium atom. And that's the execution of this octet rule we're seeing. Remember that both of these have low ionization energies, and that's why we're looking at losing, where in the case of chlorine, I'm going to change the atom has 7 valence electrons. You also see there's a lot of numbers over here. So the first thing I want to say is, remember I said these are oxidation numbers. You can't always use these as a rule. Typically when making an ion, the numbers towards the top are going to be most common, but I cannot say that with any definitive answer. What I'm saying instead is look at the electron structure and do what's needed to make it look like a noble gas as much as possible. So for the chlorine atom, there's 7 valence electrons. The effective nuclear charge is a +7 on that third energy level. So compared to the +1 of the alkali metals, chlorine atoms have a relatively strong pull. They're smaller atoms than, say, like the sodiums that are in the same period. These are going to gain electrons, these nonmetals. High electronegativity. So I'm trying to highlight the two reasons why we're seeing what we see in terms of how they behave. But again, as they gain an electron, 287 will become 288, which again matches that nearest noble gas. The good news is when we start looking at Lewis structures, Lewis dot diagrams for these atoms, you'll start to see these patterns emerge even more so. Just as a quick reminder of what all of the atoms look like, let me draw them in. And remember for sulfur that your order is 1, 2, 3, 4, 5, right? So paired up, single, 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 and then double. So we have 2 pairs and 2 unpaired electrons. This will be important down the road. And then chlorine would have 7 valence electrons. So then we see there's that one space that the 7 suggests. Okay, turning these into ions and talking about the common ion, the stable ions that would be made, again, we're going to look at that valence shell. And in general, our metals have low ionization energies, and so they're going to lose electrons. The ion that you're going to make is sodium. We're not showing any electrons because, like I said, the valence shell is the third energy level, and we went from having 1 electron to 0. I know now the outermost occupied level has 8, but remember that for a Lewis structure, the sodium represents all those inner shells. Plus, it would be a little bit misleading to have 1 dot with the sodium atom and then 8 dots with the sodium ion when it lost an electron, because it looks like you're drawing 7 more. And then the other thing we are going to need to do is we're going to have to show that there's a positive charge present when these ions get made, because you lost an electron. And we're going to put in that upper right-hand corner that charge that we talked about before. In the case of magnesium and calcium, they both have 2 valence electrons. We're going to dump both of them. The idea being we lose electrons until the electron configuration of the ion matches a noble gas. That's at least our starting point for this discussion. So in this case, we're still going to have our kernel. We're not going to show any valence electrons because that third and fourth shell are empty. And now we have to put a charge, but for these two ions, the charge is +2 or 2+. For sulfur and chlorine, it's a little bit different. Argon, there is no ion made. Let me just say that because, noble gas is already there. And you do see that there's a 0 there as a bit of a suggestion, a hint that that's happening. And then let's start looking at chlorine because we did talk about that one already. Having 7 valence electrons, you're one gain away from looking like a noble gas. So you have a high electronegativity. This happens. The chlorine atom gains in electrons, so we want to show 8 valence electrons. There are 2 things that you will see in literature. One is to use a different symbol. And the point of the different symbol is to acknowledge that we are all in understanding together that we know that the chlorine should have 7 as an atom, and now there's one more making 8 as the ion. So that for sulfur, we would also expect to see 2 of those. Now, it is also possible that when you're reading the literature that you'd also see the gained electrons be dots, because it's a little hard to say that electron, that one there, is the one that was gained or lost because, these electrons are clouds. They're moving around, they're jumping, they're switching spots. So sometimes you'll see people put a different symbol. Sometimes you'll see people put the same symbol for gained electrons. It doesn't really matter. Now, in this case, you want to put a minus. And here you'd put a 2 minus. But there's a different choice that we make here. Because now the ion is showing electrons, note that for the metals, the positive ions made, no electrons showing. We have to say all of these electrons are belonging to this particle. I just thought of a really good yes. And the way we do that is by putting a square bracket around the ion inside of the charge. So for our anions, we're going to put these square brackets, and this is our way of saying all of the electrons are associated with just that particle. This might be stirring up a question in your mind. I kind of hope it is. In the case of the metals, these metals are just losing electrons. And in the case of the nonmetals, they're just picking up electrons. Where are these electrons going and where are they coming from to allow this to happen? There is, conservation of matter to consider. The sum total amount of electrons in this system need to be staying constant. Now, if you thought that, great. If you already answered it, even better. Because that process of tracking where the electrons go and making sure they all are accounted for is ionic bonding. So we have some definitions there for what a bond is and what specifically ionic bonding is. There are several types of bonding that take place, but down here we have some Bohr atoms showing sodium and chlorine. As the electron gets transferred, we said that sodium, due to its low ionization energy, will lose electrons. We said that chlorine, due to its high electronegativity, would gain electrons, and they actually, there's a pairing that happens. That pairing is what you saw in the video with the explosion. There's a lot of energy involved in this process. So to show this in Lewis atoms, you have your sodium ion and you have your sodium atom, and your chlorine atom. And much like it shows in the animated GIF below, the way we're going to represent this is we're just going to draw a little arrow. And then we're going to show what gets created. Sometimes you'll see this plus here. This means, and, or mixture, which would make sense because sodium atoms and chlorine atoms react. And what we end up making is our sodium ion, like we showed before, and then we have our chloride ion, shown here. And this is where that bracket really comes in handy, because as you can see, it's a little bit questionable as to where these electrons on the left side of chlorine are associated. And that's why we take the step to put these in brackets to say these two ions are now ions. We've got to transfer electrons. The electrons do not belong to sodium. They are now associated with the chlorine. And also, as you can see in this Lewis structure for ionic compound, The ions are shown being right next to each other. The ion charges are showing. But this is not how you would usually see it if you were looking up a chemical online or looking up a chemical in like a book or something. So this Lewis structure is very different than the chemical formula, because you would just write sodium chloride as NaCl, no charge is shown. So this is where, again, that code, that processing of the language has to come in, where you say, ah, yes, I need to recognize that this is an ionic compound and that ionic bonding is taking place. So, which is everything I definitely just should have done on the previous slide again. So the one thing I do want to mention here is that one of the best ways to identify that a compound is ionic is the presence of a metal and a nonmetal in your chemical formula. This is, again, where the importance of proper nomenclature and writing everything out correctly gets really important, because there's a big difference between writing this as a mixture of elements and then you're on top, this is a compound, a pure compound. So again, the sodium as an ion becomes an Na+, the chlorine as an ion becomes a Cl-, and if we're drawing that as a Lewis structure, don't forget to show that the amount of electrons is now stable. Finally, as one last thing to add to this, something I usually say in class is that atoms don't have brains, they don't have emotions, they don't have thoughts, and they don't have feelings. So a lot of times I hear the explanation that, oh yes, it's a good idea for sodium and chlorine to bond because sodium has one electron and chlorine needs one electron, and so it fits. But unfortunately, the universe doesn't care about what fits. The universe does what the universe does, and it works. And we can talk about the rules that govern that. But convenience, not really a good thing in terms of the universe. The universe isn't doing this with any sort of plan behind it. It's just laws of nature enacting. Serendipity is not a common thing. So let's go through this whole process again. But now I want to talk about not sodium reacting with chlorine, but calcium undergoing the same process. I would assume that the reaction looks somewhat similar. We know that calcium is a relatively soft metal. It's not as soft as the group 1 elements. But let me just quickly draw our two Lewis dot structures for calcium and chlorine. So as they react, what we're going to see is that electrons get transferred, just like before, from the metal to the nonmetal. However, we see 2 and a +2 here, so our target ion is to make a calcium 2+ ion like we saw earlier. Let's move one of our electrons down here, and then we have a problem because due to the 7 valence electrons in chlorine, gaining another electron would eventually make your structure look like this. This would be our Cl2- ion. Two problems with that. One, we've got way, like, I don't know if we would put 1 dot now because that's the outermost energy level, or would we put 8 but to put a 2 minus, like, it's very confusing. And then second, don't forget when we talked about electronegativity that pulling an electron into a new energy level, there's no effective nuclear charge to accomplish that. That just doesn't happen. So because of those two things, this isn't going to happen. What's going to happen is exactly what we saw before, and I think this is why people frequently call it an octet rule, because it does seem to be something that governs what happens. The chlorine is only going to pick up 1 electron. So that yields a question. What do we do with this electron? You can't really leave it on the calcium because that's not making it, that's not what happens. We'll start by saying that. It will not match a noble gas's electron configuration. It is not a step towards stability. And that's really how the universe works. Everything is a step towards something else. But, like you saw in the video, it was a tank of chlorine, so there's totally plenty of chlorines present. I think what might happen is this second electron would end up transferred to a second chlorine. So in terms of our Lewis dot structure for our compound that gets formed, it would look like this. One calcium ion would be made, and two chloride ions would be made. Or you could write it with a coefficient. We understand that these two Lewis structures convey the same information, and what you end up seeing is that the overall ionic compounds that you make are still electrically neutral. We started with atoms that were neutral. We end up with ions that when you add up all the charges, you get zero. I'm not saying that ions don't have charge. I'm saying when you have an ionic compound, the overall compound is electrically neutral. So this ratio of ions that you can make can vary. It can be a 1-to-1, or 1-to-2, or 2-to-1, or 2-to-3. But in general, atoms will either gain due to electronegativity or lose due to ionization energy electrons to make ions. The process is not limitless. It'll empty until you've got an empty valence shell and then 8 below. Or fill until you've got 8, because the next one would go into the next energy level. And that the Lewis diagrams for those metals and nonmetals do change as well as they become ions. And of course, those properties of the compound as they become ions do not match what you think you know about the elements. But in general, ionic bonding occurs when electrons are transferred from a metal to a nonmetal, and you have to look at the individual atoms concerned before you're able to make a neutral Lewis formula, or a formula in general. There's one thing I forgot. If we were to write this as a compound, we would write all of the elements mushed together with any subscripts that apply to the compound. So now we've got a compound, we've got a Lewis structure for that compound, and we're well on our way to talking about ionic bonding. Thanks for watching.